thing too is that I failed to put up the accelerated reference frame problems last night. I'll put them up. You can do them over the weekend. It's not long. So, yeah.
We're still having a test on Monday.
So we're going to have a test on Monday. Your test is going to cover circular motion. It's going to cover universal gravitation, Kepler's laws. If there is an accelerated reference frame problem, it will be easy. Yes.
Is today a review day?
So today is a review day. We're basically going to take a look at anything that has troubled you about the homework, and if not, then I have other plans for solving problems that will be helpful to you.
You will be provided the masses and the radius between.
Right. I mean, if you're going to use the formula, a single equation, then you have to have all of the information except for one variable. That's a mathematical absolute, right?
Do we have to know things like the gravitational constant?
That will be provided for you like it was in the quiz. The value of G will be provided. However, at this point, it's probably somewhere tattooed on your eyelids because you used it so much. Right? So there it is. Let's see. If you want your quizzes, I have not yet graded the quizzes because Grant is taking his. However, I will have them graded by 7th period. You can wander by the media center and I'll give you yours if you'd like to take a look at it. So there's that. I think that's kind of it. At this time, I'll take any questions that you have about any of the homework you've done over the last week.
Number 59 says Halley's Comet orbits the Sun roughly once every 76 years. It comes very close to the surface of the Sun on its closest approach. Estimate the greatest distance of the comet from the Sun.
Okay. And then it gives you a little hint. Okay. First of all, take this problem and break down the information given to you. Tell me everything that is being told you by that information.
So we have a period of 76 years.
Yep.
And so we use our period equation, which would be T.
Wait. I do not see that you have paid close attention to everything that the problem has told you.
Comes very close to the surface of the Sun.
What would that mean?
I don't know.
Aha. Then what does he need in order to make sense of the information given? I keep telling you guys this.
Pictures.
He needs a picture. So how does my picture look?
We have the Sun, and Halley's Comet is elliptical around the Sun, and very close to the Sun.
Let me do something like this. Now, what does that information tell me?
And Halley gets really close to the Sun and then really far away.
Okay. A smart student at this point is going to say, let me mark that information with a variable or a number. What variable or number could I mark this information?
D1 is this one.
D1. And could I come up with a number for D1? Yeah.
You could set it at 0 since it's so close.
I could set it at 0 since it's so close. Or I could set it to the, and that would be a little more precise. Both of those will work just fine. Does that make sense? See how we're doing a simplifying assumption? I like that simplifying assumption. I like yours too, but D1 equals 0 makes the problem kind of easy. Okay, now keep going. Do we have any other information given to us in the problem?
No.
What about that hint? Do you think that at 5 cents a word, they're going to throw in a hint for nothing? It's not really 5 cents a word. What does that hint say, and then what does it mean? Yeah.
So, you you'd solve Kepler's, you'd use Kepler's third law, solve it, and then divide it by 2. Right, or multiply.
Probably multiply it by
Yeah.
2, but let's see why. What the hint is literally telling us is that this distance that you find here is going to be the average of nearest and farthest. I have everything but R. Yeah, there it is. Now, interestingly, TFE has made kind of a cottage industry out of using the alternate form of Kepler's law, which is a comparison law. If I set this up for one planet, and then I set it up for another planet, and I divide, then all these constants drop out, and I'm left with this. And you can use that to compare. That's only going to be useful if you have a reference to compare with, but hey, we do. What known reference do we have to compare with? Well, the Earth, right? The sun doesn't rotate around itself.
Oh, I thought you meant what reference point.
Yeah, no. What reference information do we have to compare with? And that's the Earth. That's right. So you could use either one of these to find the radius. When you do find the radius, plug in numbers, blah, 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 do magic, and we get radius is equal to, I forget the number, it's like 5 times 10 to the 5 times 10 to the 15? No, that's too big. What was it? Somebody did this. Yeah, and that's the interesting thing is that if you use the bottom form, you don't need mass of the sun. Which is kind of cool. You only need to know the period of the Earth's rotation and the distance from the sun to Earth. So we're trading off one piece of information for another.
Okay.
And then you need to know the period, which we do. I'm going to set it up at the bottom one. I don't usually use this bottom equation, but I really like the convenience. RH cubed over radius of the Earth is 98 million miles. Why should I know it in miles? That's silly. What is the Earth-Sun distance in meters or kilometers? 150 million kilometers. I should learn that number. 150 million kilometers. And so that gives me one point 1.31 times 10 to the 9th kilometers. Is that what you guys got? Yes, no?
I got 1.4.
Let's see here. Do this a different way then. 76.
Are the t's supposed to be squared?
Now I'm getting 6.35. Hang on just a second. Apparently I'm doing this wrong. Oh. Yes, the t's are supposed to be squared. Thank you. Right. Correct. There we go. So this would be 76 squared right here. That's my issue. So clear all that. Squared times 50 and then keep roots. 2.69 times 10 to the 10th? No, times 10 to the 9th. that better? I mean, you worked this problem yesterday.
Yeah, I think it's.
That sounds right. Okay. All right. So now, what does that give me? Well, that gives me the average radius according to the problem. And the average radius is going to be the farthest plus the nearest divided by 2. But here's where Gianna's excellent suggestion becomes really relevant. Because if we take D1 to be 0, then it makes solving for D2 a simple matter of multiplying by 2. And that gives me 5.38 times 10 to the 9 kilometers as the far distance to Halley's Comet. And there it is. So what did you learn from this problem? Several things to learn. Little small things. Draw those pictures, absolutely, because the pictures create meaning for the equation. It's not just plugging in numbers. What else?
Make assumptions very literally.
Yes. Or even simplistically, we actually did not take this literally. We didn't take it very close to the surface of the sun. We took it at the center of the sun, which was a really not correct, but it is a simplifying assumption that turns out to make a difference in like the 4th decimal place.
Do you still reference crashing to the sun?
Oh yeah. Yeah. Yes, sir.
This one is always back in the second buzzing.
Sure.
Number 10.
Number 10, how's it go?
How large must the coefficient of static friction be between tires on the road if a car is to run a level curve with a radius 85 meters at a speed of 95 kilometers per hour?
Car rounds a level curve of radius 85 meters. Oh my. So a radius of 85 meters, let's see here. No, it's not horrible, but we'll see. At 95 kilometers per hour. Now just to get a sense of it, every 8 kilometers per hour is 5 miles per hour. So, let's see, 96 divided by 8 would be 12 times 5 is 60. So we're going to take a kind of tight curve at 60 miles an hour. Good luck to us. Let's see how this goes. Okay, now what did you do?
I don't know if you
Okay,
can remember. R would be 85.
okay, yep.
And D would be, you should probably convert that to meters.
Yeah, we're going to have to get that in meters per second. That's unfortunate. Jayla, I'm going to put you on that. Can you get our velocity into meters per second, please?
And I'm getting the mass of the car.
Yep. And we have enough experience to know that often cancels out.
So, central acceleration.
Boo! Hiss!
Free body diagram?
Yes! We don't have the mass of the car, so free body diagram. Our radius is 85 meters, so free body diagram. Velocity is 95 kilometers per hour, so free body diagram. All roads lead to free body diagrams first. Now, do we want to do the free body diagram from the side or from above? From both. Nice. I like it. Oh, okay. All right, well, let's do both. If we do it from above, what forces are we looking at?
Friction,
Pointing which way?
away, opposite from the wood carpet, so that's it.
Nope. Mm-mm. Yeah,
Towards the center of the circle.
it's got to be towards the center of the circle. Now, the guess was not a bad guess, but we want to clarify here. When tires are in contact with the road, they are not actually moving relative to the road. They're just rolling along. And as they roll along, they stick to the road. So we're looking at a static frictional force, not a kinetic frictional force. If we were sliding on the road, heaven forbid, then there would be a frictional force pointing backwards. But we're not. We're sticking along the roadway. Okay? And then Also, static frictional force is going to point in the direction of potential motion. The potential motion of the car is to go off of the road, think in terms of our accelerated reference frame, right?
Yeah.
Yeah. And therefore, the static frictional force is going to have to point opposite of that direction. It's going to have to point straight inwards in order to keep the car on the road. All right, so this is our top view. And this is now, what does our side view look like?
Normal force on the gravitational force on the other.
Yep. And now you can see why we needed a side view here. And what about my frictional force?
Coming towards you.
It's going to have to actually go in towards the center of the circle again. I really should have called this a back view. We're looking at the car from the back side. Okay. Do you have our velocity yet? Ooh, that sounds small.
I don't know
How do your conversion factors get set up?
95 kilometers per times 1 hour over 60 seconds. Now within seconds.
Oh, it's actually an hour every 3,600 seconds, right? Because there's 60 seconds in a minute. Yeah.
Okay.
Okay. What else?
And then I did a second one.
Okay.
So and then I had the answer I got was wrong in the first.
Sure, I understand. But what else do I need here? I've got my hours.
Meters per. Meters per kilometer.
How many?
26.
What is kilometer? Oh no, what is kilometer? It's all about the words, people. Kilo means 1,000. That's right. 2,000 mockingbirds, 2 kilo mockingbirds. Okay. Now recompute that and tell us.
You can do.
Recompute your speed there and tell us what you get. Okay, so back to you. I've got my free body diagram. Where do I go from here?
So you can find the normal force, which is mg.
Why does Fn equal mg? What analysis gets me there?
The sum of forces in the y direction is eating the reference frame. I don't know which one's closer.
Good lad. Let's take positive to be in towards the center of the circle.
The sum of the forces in the y direction is Fn minus mg.
Good.
And the other forces.
Okay. All right, so we have Fn equals mg. He's good. Carry on. What about in the x direction?
It's only frictional force.
There's only the frictional force.
Okay. So that has to go element.
It does. And I want to show that as the sum of forces, and I'm going to call it in the centripetal direction, because it depends on where we are on the curve here. It wouldn't necessarily be y.
Oh, and so we call that FR?
Yes, or FC.
Valuable and AC.
Which is, what's the value of AC always? What's always the value of AC?
V squared over R.
Just where you are. There you go. So this is your centripetal force right here, and it is being supplied by the frictional force. What you got? That sounds much better, yeah. Okay. So far, so good. I have learned the following things. The normal force must be equal to the gravitational force, or the weight of the car, and the frictional force has to equal mv squared over r. But I still haven't answered the question, which is, what is the smallest coefficient of friction that will do the job? So we need an additional piece of information or equation or inequality. Yes,
The frictional force is less than or equal to US times
good, which is
G.
in G. Good. So now, what of this inequality? Well, it strikes me that if I want US to be as small as possible, minimum, then I have to take equality. Does that logic make sense? How about, let's do it like this. We'll do it as a direct substitution. Since Fs is in V squared over R, then I can replace Fs with NV squared over R, and NV squared over R therefore must be less than or equal to US times NV. How's that? That gives me a direct inequality. Now, do you see what I see?
You guys know that.
Ah, that's why they didn't give us the mass of the car. And do we have all other numbers? We do. 26.4 meters per second. Thank you, Jayla. Radius of 85 meters. And G is, of course, 10 meters per second squared. Now go ahead and compute that because I'm curious how much of a mu we need. Estimating this 25 squared is 625. So 625 divided by 85 is going to be about 3 divided by 10, so it must be about 0.3 is my estimate. What'd you get?
Catching up a little bit.
Oh, okay. We got 41. Yeah, 26.4 squared is 700. So it's actually larger than I was estimating. 22. This is totally reasonable for a dry tire, but in rain, your tires are not going to get that kind of a mu, and you should not take curves quickly in rain. But you need that. This is a great problem, and I recommend going back and practicing it once as a kind of standard model problem for the types of things you might need to do on a test. Okay, good. Any other questions? Okay, good. Then what I'd like to do is to do some practical computation. I have a question, and that is, how much gravitational force is there between Damani and Jesse? What is the magnitude? I've told you that all masses attract each other with gravitational force. So I am, just by virtue of standing here with my mass, I am attracting you all of you towards the center of the room. Don't you feel it? These two feel it. I suck them all the way to the front. All right, so what is the force of gravity between Damani and Jesse? See, this is a silly question, but the real question is, suppose Jesse wants to start attracting women by his gravitational force. Should he gain mass in order to accomplish that?
Yes.
So let's see if there's any hope for that plan. According to Newton's universal law of gravity, the force of attraction between them is going to be Gmm over r squared. So we're just going to have to do some estimating here. Taking a look at the two of them, what would you estimate as the r between them, center to center distance? 1 or 2 meters, somewhere in there. That's right. Remember that a meter is from center to fingertip, and that's about it. So we're going to take r as 1 meter. And how about the masses here? What's your mass in kilograms, Jesse? 67, let's call that 70. And Damani,
Is it 2.2?
2.2 kilograms, pounds in a kilogram, that's right.
So it'd be like,
We'll call that 50. And then this is going to be 7 times 10 to the minus 11, because we're doing just one sig fig here. Some quick estimation. And what is 5 times 7? 35 times another 7. That's too hard. Let's do 40 times 7. 265? Okay, so that'd be 265 times 10 to the minus 11 times 10 times 10. So it'd be times 10 to the negative 9 divided by 1 squared is 265 times 10 to the minus 9th newtons, or 2.65 times 10 to the minus 7 newtons. See, we did that without any calculators. That's not much of a force, but how much of an acceleration does that provide?
Actually, I think that's 240.
Close enough. We're looking for just one sig fig, really, so it's really 3 times 10 to the minus 7 newtons. That'll work. All right, how much of an acceleration does this provide? Well, if we set force equals mass times acceleration, and we're going to look for Jesse's acceleration towards Damani as a result of the gravitational attraction, then, let's see here. And we're assuming no frictional force, which is ridiculous, right? So in point of fact, the frictional force is obviously going to overcome that. Whatever force of attraction here, he's obviously stuck. So in reality, there's no net force between them because of friction. But let's pretend there's a frictional surface going on here, and now you're going to slide towards Damani as a result of gravitational attraction. Okay? So let's see how long that would take. We've got an acceleration of 70 kilograms, did we say? Times your acceleration. And so we divide both sides by 10 first, and then by 7. 3 divided by 7, that'd be about a half. So that would be 0.5 times 10 to the minus 8, or 5 times 10 to the minus 9. Meters per second squared is the acceleration. So, his mass. Yep, I used his mass.
After P was like the first equation, and why would also put it equal to mass?
Because force is always equal to mass times acceleration. Once I've computed a force, I can now set that equal to mass times acceleration. Once I've computed net force, I should say.
What is the thing, the number next to the,
Which one? Here?
yeah,
Oh, 50 kilograms.
yeah, what's that one?
70 kilograms.
No, for like,
7 times 10 to the minus 11.
okay.
The gravitational constant is 6.67 times 10 to the minus 11, then I just rounded it.
Oh,
Because I was in a rounding kind of mood. Changing it up, that's right. All right, so we wonder how long would it take for Jesse to reach Damani starting from rest? Okay, so we say delta x equals v0t plus 1/2 at squared. And therefore, the delta x between them was 1 meter, is that right? So 1/2 of 5 times 10 to the minus 9th times t squared. Multiply both sides by 2, divide both sides by 5, and divide by both sides by 10 to the minus 9th, and you get 0.4 times 10 to the 9th, or 4 times 10 to the 8th, equals t squared. Square root both sides, and get 2 times 10 to the 4th seconds. 20,000 seconds.
Did you say lost it 0?
Yeah,
Okay.
because they're starting from rest. 20,000 seconds, that's not very enlightening. How long is that? Let's see, every 3,600 seconds is an hour, so it's going to be somewhere in the neighborhood of 6 hours. It would take 6 hours for the two of them to come in contact with one another, something like that. Okay? Now, why do I go through these computations? Well, one reason I go through these computations is because it's interesting and fun. We imagine Jesse now decides on a program of weight gain in order to increase his gravitational attraction towards London. And the question is how much mass would he need to gain in order to increase that acceleration to like 1 meter per second squared? And the answer is kind of obvious. He would have to increase his mass by a factor of about 10 to the 9. He'd have to become 1 billion times heavier just to be gravitationally attractive towards women or men or cows. Yeah.
If two astronauts on the ISS were to chill in one spot for 6 hours and the other part,
Yes.
would they collide after 6 hours?
Assuming no other objects of mass. But in fact, what happens instead is that there are other objects of mass, plus they don't like to drift like that, they'll actually clamp down the roots. And so we call their situation on the ISS, we don't really call it zero G, we call it micro G, microgravity. Because since the ISS is free falling around the Earth, the astronauts are free falling with it, so they experience a fictitious force pushing outwards. As a result, they experience essentially no force from the Earth, no gravitational force from the Earth. And now what takes over are all the little tiny gravitational forces going on inside. So it's a micro-G environment. Weird things happen in micro-G. If you light a candle in microgravity, the flame is spherical. Because hot air no longer rises. Which is kind of wild. If you spill your coffee in zero G, it's a mess. Little droplets everywhere.
That's terrible.
And worse, if you're floating in zero G and you grab a hold of a wrench and you try to turn a nut with the wrench, the nut might turn a little bit, but you're going to go the other way. So one of the things the astronauts have to do is to remember at all times to clamp themselves down because they can't rely on gravity to clamp them to the floor and friction to keep them steady as this. So yet your intuitions are all wrong.
I have to go back to Earth.
Now the reason I bring this up is sometimes the internet will lie to you. I don't know if you've noticed this or not, but occasionally there are lies on the internet. And sometimes they're just people who make mistakes. And there is one example of that I'd like to show to you. And it has to do with an experiment called the Cavendish experiment. I mentioned this to you, but I didn't teach it to you, and I'll do that at this time. The Cavendish experiment was also called weighing the Earth. Because what Cavendish was really doing is he was trying to use small toy masses in order to proportionalize it to the Earth. He thought of himself as figuring out how heavy is the Earth. What he was really doing implicitly is finding the value of the gravitational constant G. So let me show you how that worked. What Cavendish did was he took, here's a side view of his experiment. He took a long beam, you might think of it as a meter stick, for example. And on this beam, he hung two masses. I don't remember what they were originally. His original paper is online. But we're going to call these M, and the masses were equal. And he took this beam with the two masses, and he put it on a very light rope, really almost like fishing wire. It was made out of metal. And the property of that was that as you turned it, there was a slight force pushing back the other way. Have you guys ever like twisted yourself up in a swing and like, oh, and it turns back? Yeah. So this was the same kind of a thing. It's what we call a torsion spring, so that there was, as you turn it, there's a really slight force pushing back the other way. Then, let's do the top view now so we can see what happens in the top view. In the top view, here is my beam with the two masses, M1 underneath. M1 like that. He puts this whole thing in a really large wooden chamber so that it's isolated from wind drafts and so that essentially kind of all of the other masses around it cancel out. And then he comes along and after this thing has settled down, and he leaves it there for like half a day so that all the motion completely settles out. Then he comes along and he puts another large mass, I believe it was a cannon, here and here. And when he puts the large masses here and here at equal distances, what happens is the gravitational force between these masses now attracts them, and as a result, there is a slight motion in this direction. But when there is a motion in that direction, then the rope itself starts pushing back. So at some point, the two hit equilibrium. And when they hit equilibrium, then there is a slight deflection from the original. And yet, he had the chamber set up carefully so that he could use a telescope to measure that amount of deflection, which was really small. It was like a couple millimeters. And as a result of that, he could find the force between the two masses. So that was the Cavendish experiment. Nowadays, it's done slightly differently. Because of the deflecting force, the whole thing kind of oscillates like this. And so we actually measure the period of oscillation and use that to figure out the gravitational force. But the principle is basically the same. All right. So that's the Cavendish experiment, and as a result of the gravitational force canceling out the spring force, then that leads us to a measurement of the gravitational force. And since we know the distance between them and we know the masses, therefore we can calculate the value of G, and ta-da, we now know the mass of the Earth also. This happened 117 years after Newton provided his universal gravitational law. So for years and years, all we knew was the product of G times the mass of the Earth. And we didn't know either value separately. Well, I was looking for videos of this because I wanted you guys to be able to see it, and I was not able to find any really good videos of it. But I did find one high school class that thought they were doing the Cavendish experiment. And I want to show you the video, and you tell me what you think is wrong with it. Let's see here. This is the one.
I'm looking for a girl. Her name is Julie.
Blah, blah, blah. This is also... Okay. So here we are, Cavendish experiment, right?
Is it floating?
There's a mass. See the orange in the middle?
Yeah.
There's a wire attached to that.
Oh.
Somebody tell me why this cannot possibly be measuring gravitational attraction.
Because it's another force.
Let's see all that. But how do you know that? How do you infer that? Let's see all that happen again. So this is obviously in high speed, about 5 times speed. What do you notice about the motion of the beam?
There's a magnet. There's two weights. Or
Don't know.
It's hitting them, it's hitting
It is hitting them. One more time. Don't try to tell me what they did wrong. Tell me how you know that this can't possibly be gravitational force causing this motion. We're not sure what they did wrong. There could be a lot of different explanations for what they did wrong. But we know it's not gravity doing this.
It's too fast for you.
It is way the heck too fast. What did we calculate? How long would it take for these two on a frictionless surface to find each other?
6 hours.
About 6 hours. How long did it take for this thing? Let's do some distances, some quick distances. Tell me the starting displacement right here, about just roughly, how far away is the mass from the dumbbell? A foot, something like that. The whole stick is presumably a meter, right? Which means that this guy is about 1/4 of a meter, maybe 1/3. A foot is a really good estimate. Okay? So now we have a foot, and then how long does it take for the whole thing to swing and hit? It took 3 seconds of video time, speeded up by a factor of 5, 15 seconds for that whole thing to swing around. The gravitational constant would have to be, let's see, 15 seconds is what part of 6 hours? A fourth part of a minute times 6 hours. The 24th part of a minute times 60 is going to be about 1/1200th. That's right. This gravitational constant that they're measuring is 1,200 times too large. You see what I'm saying? And we can read all that off the video without having to do any fancy computer measurements or anything like that. We can just eyeball it. Now we can come back and say, well, what are some possible explanations? What do you think might possibly have gone wrong? What are they actually measuring? Why is this thing twisting?
Maybe the strings are twisted.
Yeah, maybe there's an initial velocity caused by an initial displacement of the string. Do we see any evidence of initial velocity going on here? Look at what we've got when the video starts. Look at that, it's already moving when the whole thing starts. I don't know what they're doing with the masses. They don't seem to be touching them. Or they touch them, but they don't seem to be doing anything. You know what I'm saying? They're there, they go over, they put their hands on the masses, be healed, but they don't actually do anything with them. So I don't know what the point of that is. Whatever this is, it's not actually measuring
Why didn't they
the
do that?
gravitational force.
They put the weight down so they let the rope set.
Yeah.
In their original experiment, the second, like, there were the two masses on the string, and
Yes.
then he took two other masses and
Yes.
put them
Near.
near.
Yes.
Okay.
He comes along and he puts them near. Like that.
Okay.
Good. Well, do you have any, we have about 5 minutes, do you have any last minute questions before we call it a week? Good?
So
Okay.
where's our test starting from?
It's going to be just, well, I say just, it's going to be just this chapter,
Okay.
but as you know, we always end up with review stuff because
Right.
so there's going to be cars going around curves, and there's going to be objects on strings, and there's going to be planets, satellites tracking one another, etc. But unfortunately, Jesse is not going to be the Mani satellite. All right. Well, I will have a great weekend, and I will see you on Monday.